Hello everyone, welcome to Aspen Plus tutorial video, and today I'm going to talk about drying process. And specifically, I'm going to try to simulate a drying process of non-conventional component, which is coal using RSTOIC block. Before I begin my videos, I would like to apologize for not uploading my usual videos earlier because I've been so busy with a lot of things like exam grading, uploading scores, marks, and then symposium as well as industry project. So I was a bit preoccupied with those things in the past 3 or 4 weeks. And this week I have quite maybe some free time which I can use to make my own my Aspen video. But unfortunately, this is gonna be a very short one because I haven't had time, I guess, to do a thorough research or maybe try to pick up interesting Aspen Plus design problem for all of you guys. So yeah, let's begin. Okay, these are our design problems. This is a very simple one, but what I want to highlight here is the my way of thinking on how to simulate this process. I guess my thought processes. For this design problem, I have 1 kilogram per hour of wet coal. Okay, they are dried in the at 120 degrees Celsius. Okay, we will try to simulate them using a stoic block here at 120 under 1 atmosphere pressure to remove the moisture. And then I did this one before, and what I found is that the simulation is converged, okay, only when I use the stoichiometric reaction like this, okay, where I have 1 wet coal react to form 0.95 dry coal plus these weird numbers of moisture. And you have to understand that to use our stoic block, you need to know your reaction stoichiometry, and it has to be correct. As well as you need to mention what's the fractional conversion of this particular reaction. When talking about drying of non-conventional components such as biomasses or maybe coal, there are a lot of ways for people to do this. I saw people using a vapor liquid separator to simulate the drying process, where they just have one stream containing dry coal plus water. Dry coal is non-conventional component plus water, and then they put it in the vapor liquid separator, set 120, 1 atmosphere, and then done. You can do that. There's also a simulation where people use R yield to where they need to specify how many percent of the incoming feed, which is wet coal, turn into moisture plus a dry coal. And then the third one is the one that I want to try to solve today, which is using RSTOIC. And as I mentioned, it requires me to input the reaction coefficient as well as a correct reaction pathway, I guess, reaction equation, as well as my fractional conversion. Yeah, I don't know, but all of this will give you a simulation will converge definitely if you input it correctly. But I think the only difference here is probably the enthalpy. Mass will be, if the simulation converge, mass balance gonna check out. But I think the only difference would be the enthalpy flow. That's what I think will be the difference between these three processes, I guess. Now, in this video, a few things that I want to bring forward. The first one here is how can I model the drying using a stoic block? Because drying is just a physical process. I don't need to input the reaction and reaction stoichiometry. This is number one. Number two, why the reaction stoichiometry is kind of weird. When I say weird here, it's not like it's just these numbers is a bit unusual because I have a lot of like decimal points, and normally you will see like a reaction coefficient of 1, maybe 1/2, 2, 3, or whatever, right? But this one is a bit weird. And then if you see here, These are okay numbers. When I say okay, it's like a normal one. And these are also okay numbers, but this one has a lot of like zeros or numbers behind the decimal point. So why? That's the second question. The third question here is, if I want to model the reaction using RSTOIC, obviously the reaction will be simulated. To do the calculation, you need to know what is the mole, the incoming mole flow of the reactant. But in this case, I'm dealing with a non-conventional component, which is coal. So how can I know the molecular weight of this non-conventional component? So those are the three things that I want to highlight in this video. Not so much about the process itself. Basically, my thought process. Basically, I want to highlight my thought process when I do this simulation. So to carry out the simulation, I'm just going to use stream class of MIX CINC, basically the stream class that deal with a conventional component plus non-conventional component without particle size distribution. I'm going to use RSTOIC for my thermodynamic property method, HCOALGEN and DCHARIGT correlation to give me information about enthalpy as well as density of my coal. All of this information are taken from sources, which I will show it to you in the next slide. And then I'm going to assume all moisture is removed or vaporized. These are just the input that I put in my reactor block. So basically, if you put this number, you will get simulation converge, but that's not the main point here. The main point here is how did I get this number? How did I arrive to this particular number? Okay, moving on. As I mentioned before, coal is a non-conventional component, so you need to give information to Aspen about the molecular makeup or elemental makeup of the coal itself. So these are the proximate analysis, ultimate analysis, as well as sulfur analysis. And for your information, this table are taken from this document. If you have your Aspen Plus installed on your desktop or computer, you go to C and then go to your program file and then just go to this pathway, and then you will get to this document, which is a model for entering flow coal gasifier. This document are made by Aspen, so you can just go and check it out. But the only, all of it are the same, but the only difference here is Aspen use 0.28% of coal, which makes sense because coal does not have a lot of moisture. But I decided to change it to 5. I mean, it doesn't really matter, I guess. But this is just for showing you maybe different numbers. Now, knowing the moisture, if I know my moisture is 5%, right? If I have 1 kilogram per hour of wet coal, logically speaking, I would have that wet coal, that 1 kilogram per hour of wet coal would consist of 0.05 kilogram of water, and the remainder, which is 0.95 kilogram, should be dry coal. That's how it is, I guess, because the moisture is 5. If the moisture is 10, then it's going to be different. So when I input my information in the Aspen Plus, I would expect to have something like this. Okay, 1 kilogram of wet coal forming will give like a 0.05 kilogram of moisture plus the remainder is dry coal. That's it. Okay, moving on. Yeah, as I mentioned before, the one that gave me a converged result is reaction number 2. But first, I want to show you the first reaction where I have 1 wet coal react to form 0.95 dry coal plus 0.05 moisture. Okay, you might be wondering why. How did I get this number? I mean, if you remember before, I have wet coal forming 0.95 dry coal. If you remember the pie chart before, I'll get 0.95 dry coal and 0.05 moisture, which kind of makes sense. And then, right? I mean, there's nothing wrong with it from the, I'll say, first look. But when I do the simulation, it doesn't give me a correct result, and the simulation gave me error, which we will try to look later. And then I did my own internal calculation, and I input the new correlation or new reaction coefficient, and I get a converged result. And then we can try to analyze the result and come up with some sort of like conclusion why these are the correct one, why these are not the correct one. Okay, that will be all for the introduction. So let's move on to our simulation. Okay, everyone, I have my Aspen Plus ready here. Okay, the first component that I'm going to input is just water because it's a moisture. And then I have to input a non-conventional component, which is a wet coal. And then I have to input the other one, which is a dry coal. Both are non-conventional component. Okay, moving on. I just hit next. RSTOIC. Where is it? It's not here. So go here. Okay, hit next. I'm gonna use what's it? HCOALGEN and then the coal IGT. Okay, if you don't know what the heck this means, please check out my earlier videos and to know what this option code means, as well as what this thing means. I will put the link to the videos in the description box. Okay, these are the information for wet coal, but I need to specify for dry coal as well. The same thing. Okay, in this video, I'm not going to change this because that's not the main point of this video. Main content of this video. I'm just going to put it as it is, and then hit next. Go to simulation. Okay, it's going to be a simple one. Before that, let me change my stream classification. Go to setup, go to specification, choose this one, and then go to flow sheet, go to reactor, RSTOIC, dry. I have what is it called? Wet coal, and then I have a dry coal. I'm going to align it a bit, make it nicer. I should be okay. Okay, these are my process flow. It's very simple. The next one is to specify the component, the incoming flow. There's nothing in the mix substream. Just go to the non-conventional. So 30 degrees Celsius. Pressure is 1 atm. Mass flow is 1 kilogram per hour of wet coal. So here you need to specify the component attributes. Moisture is 58.01, 26.46, and then 15.53. And then ultimate analysis, ash is 15.53. Carbon is 74.05. For coal, it's not that surprising to have a lot of carbon. Elemental carbon, nitrogen is 0.71, chlorine is 0.37, and then sulfur is 1.77, oxygen is 1.32. And then lastly, you have a sulfur analysis, which are 0.59, 0.59, and 0.59. Okay, I'm done setting up my my incoming feed or incoming stream. Just need to specify this 120 degrees Celsius and 1 atm or 0. You can do 0 if you want. It's the same thing. So go to reaction, click new. As I mentioned, we're gonna use the reaction 1 first, just to show what happened. So I have a wet cold 1. I have a dry cold 0.95, and then 0.05 of moisture. Well, I assume like 100% of moisture is removed, so I can just assume everything fractional conversion of wet cold of 100%. And that's it. Just hit next and then see the result. Okay, you will see there's an error here. Okay, if I check my status, let's see. Okay, these are the errors. So let's go to here. Oh yeah, before I forgot. Okay, there are 2 errors here. Okay, the first error is component attribute is missing for dry cold. I supposed to do that. I always forgot to do that. So just go to component attribute. Nonconventional should be dry cold. Attribute is proximate analysis. So here, I don't want to waste time. So what I'm going to do is I'm just going to copy this thing, but without the moisture, because after the dry one does not have any moisture anymore. So let's see. I think it should be here. Okay, do the same ultimate analysis. Where is it? Okay, here. Copy and then go to here. Paste, and then ultimate analysis is 0.59 for all. So I don't have to copy and paste because I remember the number. Okay, then you can hit next. You still get error, by the way, but this error is, you will have only one error. So if you check here, they will there's a difference in mass flow in to mass flow out. So basically, the mass balance is not conserved, and then they ask you to check stoichiometry or molecular weight. Okay, let's go back to I have the result actually, which I have compiled in my slide. So let's go back to our slide first before I correct everything in here. Okay, these are the simulation results for reaction 1, where I have 1 wet cold react to form 0.95 dry cold plus 0.05 water. So the incoming stream, no surprise here, we only have 1 kilogram per hour of dry cold, but of wet cold, I'm sorry, but the going out, the stream exiting the dryer reactor have 0.95 of wet cold, which are similar to the pie chart, if you remember, but this one is not the same. Which is I'm supposed to get like 0.05 kilogram per hour, but here I got like 0.9. So incoming stream is 1, so outgoing is around like what, 1.8 kilogram per hour. So mass is not conserved, which is the reason why you get error here. So how to do this? So it's quite easy. What I'm going to do is, if I need to find what is x here. So if 0.05 give me 0.009, what value of x will be 0.05? So you do the math, just multiply, and then you will get this number, and these are the number that I will input in my simulation. So, okay, I'm going to use this information. I'm going to input the new reaction and we will see the result. Okay, these are my Aspen Plus. I'm just going to close this one, close this one, close this one. Okay, just go back to my reactor block, go to reaction, just edit the information. So this one, I'm going to use 0.0027754. Everything else is the same. Just hit next. and then you should be able to get a converged simulation. So as you can see here, I get simulation conserve. I don't know why I keep saying converse. I don't know why. Okay, I'm not going to show you the result here, but I'm going to show you the result in the slide, and I will give you the main take-home messages. For this particular video. As you can see here, these are the simulation result for reaction number 2. If I use this reaction number 2, I will get a converged simulation, and I will get the correct outcome in terms of like mass and energy balances. So the main take-home messages here is when we are dealing with a non-conventional component and user, or we would like to convert non-conventional component to conventional component. In this case, we are converting non-conventional component, which is a wet coal, into dry coal, which are still non-conventional, but you have this water, which are conventional. We have to understand one thing. To convert non-conventional to conventional, Aspen Plus would regard 1 gram of non-conventional sample is equal to 1 mole of non-conventional samples. That's the reason why if I put 0.95, it is a correct one, because 1 gram, 1 gram is equal to 1 mole. So 1 kilogram is 1 kilomole. So 1 kilomole. So if I want to get 95.95 kilogram of wet coal, just put 0.95, because 1 gram is equal to 1 mole for non-conventional is equal to 1 mole of non-conventional. But for the non-conventional one, I think the simplest one would be to use this approach. You just choose whatever numbers, and then obviously they will give you an incorrect result, and then you just do this approach, and then you will get the correct coefficient. Take home messages here. If you want to convert non-conventional to non-conventional, you have to remember 1 gram of non-conventional is equal to 1 mole of non-conventional component, which is coal in this case. Okay, let's see. I think that's pretty much it, I guess. So yeah, if you like the videos, give it a thumbs up. Consider subscribing to my channels. If you have anything to say, just put it in the comment section below, and I will see you guys again in the next video. Bye-bye.